So today we're going to go through some of the basic steps for mining complete mitochondrial genomes and doing a basic phylogenetic analysis of these. So eSearch from the NCBI eUtilities set of tools, command line tools which are interface to NCBI. We can do a text query much like we would do on the web interface. So we have this entries style text query in the same format with the fields that we are searching are in the square brackets, and these can be nested queries. So we're searching for a particular insect family, either mitochondrial or mitochondrion. One of these is a predominant, I forget which, and then complete genome. We can set date limits if you wish, and then we part this into the efetch command, so the output of this first command, which is eSearch, is just we'll have a look. We can see exactly what it looks like. So just run this part first. Well, this is the output, and we have 70 entries, but it doesn't actually return the entry itself. It is just the kind of the index or something. So we need actually the efetch. We need to pipe this into the efetch to actually get the sequences themselves, so we can obtain GenBank format and then put that into a file with the forward arrow. Okay, so the output of these two commands we put into this file here. Let's take a look. And we can see the full GenBank format, and these are, you can see long sequences, so these are mitochondrial genomes and the translations of the individual genes. Okay. So the organism field is various fields in GenBank format. And you can see organism here, which has the taxonomic assignment given by the user. Typically this is for mitochondrial genomes, this is a full genus and species, but sometimes, particularly insects, sometimes you'll get genus only and an ambiguous species level, but we can grep for this field sort, and then this puts a list of the species we've returned into this file. Not a particularly important step, but it's useful to track such things. So let's have a look at this. We have these species here, mostly, and we can see one here, one identified at the species level. And usually useful to have an outgroup. In some ways it's better to have multiple outgroups, but for simplicity in your analysis, I usually just use one. Some software only accept one outgroup in some analysis. and you can obtain this as a single sequence. So you need to determine what is a suitable outgroup for your particular taxon of interest, and then we can just cat this, so this attach the single outgroup sequence to the others for. So we have complete outgroup and in-group. Okay, next, so GenBank format, incredibly verbose. We only need certain things from this, and I'm opting to use the protein translations for each individual gene. For this one, I don't actually see DNA has been given. I don't know, does, of course, the DNA at the end, but for the individual partitions, we have a protein translation, and these can be very easy to align, and usually sufficient information content in these for most purposes. So I'm opting to use the translations from these GenBank full files. So I have a Perl script to do this. Let's have a look at this. Okay, so now, yeah, one thing I had to do with this is to standardize the gene. So this actually uses the annotation, which is always a bit of an issue. So I had to actually standardize these gene names, because it is different fields this might be assigned to, and there's various ways people will write a gene name, like an elongation factor might be written as in various different ways. I think actually is a nuclear gene, but for mitochondrial genes, yeah, these can be written in different ways. You know, the complete mitogenes are a bit more reliable, and particularly the RefSec ones, but still, this is something to consider. And so the GenBank full format is separated, is delimited by the two /. And there's a lot of various fields. Mitogenomes will usually have an accession occasionally. You may have problem. GI, I think, has now been discontinued by NCBI. Taxonomic name is usually in this field. In addition to, so this will be the tax ID, which is a number given by NCBI to each taxon of various rank. Organism has the usually species name followed by the lineage. But I'm parsing actually the protein sequences. In addition to the DNA, where available, and these various so is parsing protein ID field, and these are the various fields which may also contain a sort of the product name. But particularly we're looking for the translation from the flat file and putting these into individual files. So this is sort of sorting the genes according to the annotated name. Okay, so let's try this script. Firstly, we delete the previous run. Let's look at the output. And we have here we have the DNA also. Let's look at call 1, and yeah, we can see the translated protein sequences. This particular script is given the G name as the after this species. So one particular file, one particular DNA, I will use it later. So I just keep that here. Otherwise, it can be deleted. So we have protein sequences all sorted into according to which gene they are, and now we need to align them. So this is not a particularly big data set, so this should be pretty quick. But I'm using math to align these, and this is a loop. Although I'll put this thing in here which parallelizes these, so it runs multiple instances set by the number of CPUs here. So let's try this again. Delete the alignment, previous alignments if previously done, and then remake them, which we do that commonly as part of the process of improving and refining our analysis. Okay, seems very quick now. So we have a bunch of alignments. Let's have a look. Yep, looks fine. And we don't really bother trimming these, I don't think. Okay, so next is to concatenate these, which is to attach all the different genes together. So I have a script I've written for doing this, and it's worth also looking at the considerations for these. So this script takes the input files after this switch, and this variable or array, it might be called, have been put into this. This contains all the file names here. So this command searches the working directory for all the alignments. All the alignments start with this and end with this, and here star, this is a wildcard, so this can take on anything, any strings. So we're looking for all the alignments and listing them all into this variable here. You can see these all have the CLO extension, cluster omega has done so. So those go into this object and are hence listed here. We're going to remove that string at the end. So important to consider missing data, and this, because there's different points at which you may use missing data, and these need to be, need to be consistent character. So now I have this. I set the missing data character when this is ever used. So if one particular gene is missing from one species, it'll get the missing data character in that part of the alignment. There shouldn't be any missing for this in this particular case. Mitogenomes are in principle have all the same number of genes. So let's run this one. Don't see any big problem. This should give us a super matrix. Oops. Okay. So this is a aligned supermatrix. So we'll look at the length is 3,761. Okay. Now, when you have a supermatrix, we also need a partition file, and this script will write a partition file, which so yeah, 13 should be 13 protein coding genes in the mitogenome. And the start and end positions are given. These are written by this particular script. By the way, I intend to provide links to all Perl scripts that I use in these videos. Okay, so we should have 48. Yep, so 47 in group and an out group. Now I just need to delete. I made this note. I need to delete 2 species. For one being it's just ambiguous. I'm not sure what it is, so it's a bit difficult to use later. And the second one, for some other reason, I need to delete. I'll just manually do this. Okay. So we need to set the model to be used for each partition. And now this script I've used it puts protein in there, which is not exactly what XML wants to see. So this is the model we need for mitochondrial genomes is mtREV. So we'll use sed to replace the protein with the correct model. Now this is faster format. Faster format has the arrow, the sequence label, and then the sequence itself. XML version 8 uses Phyloinformatics format, so we need a format conversion script. There's some tools you can find to do this. I have the script here for doing this. So Phyloinformatics format is a bit somewhat different. So look, it has counts at the first line. So these are the number of taxa, and these are the number of characters. Now this would make sense a long time ago when there's a lot of more manual checking of your files, but this is becoming less in the big data era. We don't really visually look at files so much, so this will probably be phased out. And I mean, this file probably wouldn't even, some genomic matrices wouldn't even open, because in many text editors it would be too big to view. So I expect people will stop using Phyloinformatics format, I think. XML 8 version 8 does use this. Finally, the tree search, and I don't think I've already done this. I don't think I'm going to repeat this. So I've done so this is only 48, about 50. about 50 species, complete mitochondrial genomes. This for a bootstrap. This will take a few hours, and I've run this already. So MPI run. So this is done in parallel. The bootstraps are done in parallel, and there's then the unbootstrapped effectively is separate threads done for this. We need to build a MPI specific version of XML to do this. Set 500 bootstrap. Right, we need our partition file, and we need to set the model on the command line. Although this is I think XML actually looks in the partition file and overrides this, and need the output also. Now, okay, so I've actually done this already. Now, often I have the genus and species names as the IDs, but for checking the tree, it's usually good to add some extra taxonomic information, just like you want to check if subfamily and tribe are monophyletic and so on. So I have a Perl script to attach these strings to the NUIC output tree, and we can have a quick look at the tree. So this is I'll use this as a backbone tree. So yeah, as I say, genus, species, then I have a Perl script just to attach these extra strings, so you can check for. You can see this if a string ends ini, this is like a tribe. Then if it ends inae, that's usually subfamily. At least in insects. I don't know the convention for other things. But generally, this tree looks okay, and but we can see some low bootstrap support at the base is pretty common. So this is certainly not finalized. I'll need to incorporate some additional information. So this is an interim tree that I will use for, but this does needs a bit more work. So there's different things I can do so I can add maybe some nuclear markers in addition. That might improve things a bit. So there's some basic steps to construct a phylogeny from complete mitogenomes from mined data. So I set the one consideration I just mentioned. I think MaxML will do a model test, and although I'm not sure that is relevant for my mitochondrial genomes, which they may have a specific model, but you can, if you're doing nuclear phylogenomics, you would do a model test for each of your partitions. Okay, but this gives us a reasonable backbone tree, and other steps in this project I will discuss in a later episode, particularly integrating the DNA barcodes. Okay, so